Here we go.
I wonder how many like people name it for that, because I feel like it's more than you think.
There's a registry.
Penelope?
Yeah.
It's becoming a more popular name.
That's the first time I've heard it, but I feel like it's more common than you think.
Yeah, I've always liked the name, but that's pretty obvious because I named my kid that name.
Wait, that's your real name?
Penny's full name is Penelope.
Oh, I didn't know that.
Yep. Just like Xander's full name is Alexander. But the reason why I did that was mostly because kids are kids, and they like doing that whole. I've had too many kids now, like teenagers, who are like, you know, they'll be Joey to me forever. You know, Joey, 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 Joey. And then their senior year, they'll come in, and I'll be like, hey, Joey. And they'll be like, it's Joseph. And I'm like, oh. Hello, Sir Joseph. Very nice to meet you, sir. I tip my hat to you every time you walk in. So I figured if I name my daughter Penelope and my son Alexander, then if they ever decide to change their name, it's already done. Like, they don't have to legally change their name ever. And you can always have a nickname. So, although it would kind of break my heart if my son was ever like, I'm Alex now. I'd be like, what? No! I know too many Alexes. Okay. So, here we go. And it's not about the name. Every time I would never name my daughter Caitlin because I know when I see the name, I just used you as an example. When I see the name Caitlin, I think of you. Or I think of somebody else named Caitlin that I've taught before, and I've never taught a Penny. And I've never taught a Xander. So, like, when I think of that name, I want it to be just my kid, you know?
So Triton is off the table.
Triton is off the table. And before now, it was on the table. You're my first one, my first Triton, just in case you were wondering about that. All right. So this is the empirical rule. The empirical rule is for bell curves. They call these normal distributions. The empirical rule is this right here. It says that, so the mean, can anybody think of a situation where, like, a data set that would be a normal distribution where most would be in the middle, and then you'd have some oddballs that are at either end?
Maybe you know,
Yes, weight is a great example. You really needed to dance into that one, didn't you? When you go, maybe. Roll this one out, Triton. All right, so here is that mean. Right in the middle, you got your average, we'll say weight, average weight. For everybody, most people are in the middle. You got some people who are above average with their weight, some people who are high above average with their weight, and some people who are way low with their weight. We call these people out here on the very edges outliers. And this tells you with a standard bell curve, what percent are there. So this is 1 standard deviation from the mean, plus 1. This one right here is minus 1 standard deviation from the mean. This one's plus 2 standard deviations from the mean. This one's plus 3 standard deviations from the mean, and so on. One of my freshmen today was like, why do you have to make videos for when you're gone? And I was like, because my sub doesn't necessarily know my subject. And they're like, my sub can probably teach it. And I was like, I don't know, that'd be fun to be like, just teach AP stats. You know probability, right? Permutations, combinations, everybody gets it. Okay. All right, in a survey, the sample average height of women in the United States was 64.2 inches. With a sample standard deviation of 2.9 inches, the data was normally distributed. Every time you see normally distributed, I want you to think of a bell curve. So draw a little bell curve and find out how much you suck at drawing little bell curves. Anybody think they're amazing right now? Let's see it, Triton.
Let me show you. Look at that bell curve.
Ooh, anybody got better than that one?
Oh, yeah?
Does somebody just under a sleeping bag is what he drew?
At least mine's not double sided. Why do you have 2 lines for your bell curve?
Because one was too far. These are my notes, not your notes.
Ooh. All right. So in the middle is 64.2. Because that's the average height of women. And then we got a sample standard deviation of 2.9. And we need to find out who's between 58.4. So here's 1 standard deviation. Here's 2 standard deviations away. I'm going to draw these in. If I add 1 sample standard deviation, if I take 64.2 and I add 2.9 to it, I get 67.1. Do you guys understand why I'm adding and subtracting 2.9? Because that's the standard deviation. This one down here is minusing 2. That would be 61.3 minus another is 2.9, right? Yeah. 58.4. Just a quick 28. Subtract 2.9. Jump 40. Okay. Now we're trying to figure out who is between the area between 58.4 and 64.2. So that means we're trying to find out this area right here. And if you compare it to the empirical rule, this is, do you remember when we did the empirical rule in Intro to Stats for the 7 of you who took Intro to Stats, and we had like the big bell curve that was drawn on the paper and we wrote all of this out? So we're looking for between this one and this one, which would be 34% plus 13.5%, which makes what?
7.5.
So if the United States truly is a bell curve, then about 47.5% of women should fall between those 2 heights. Okay. So this is something on the bottom that you did not learn in Intro to Stats. This is called, this is the best name of a theorem ever. It is spelt like this. And this is pronounced Chebyshev's. Okay, not chubby, Chebyshev's. Chebyshev's theorem. Everybody say it. Chebyshev's. Yeah, Chebyshev's theorem. Finish it by just blah. Okay, so it says that in any data set,